Good evening, good evening, good evening, good evening. If you can hear me, let me know. If you can't, too, let me know. If it's loud and clear, you can draw my attention. I'm going to, I will straight away adjust myself so that you can. Your response to help me know how your network is, the speed of your internet. And okay, all right. I'm already sharing the screen. Yesterday we learned about the three schema architecture, right? We also learned about data independence, and can someone flex with the things they learned yesterday? Can someone flex with what they learned yesterday? Any aspect of the whole thing? Anybody? And I also I'll be joining. All right. If you don't have anything to say, then I guess I'll ask one question. What do you think? So with yesterday's session, I think there's one quiz. Or was there a quiz? Okay. There is no quiz on this one. Okay. Okay, so today too, we are going to start another and probably enter into the next topic. So yesterday we talked about you're kind of saying, as I was saying, data models, data models, and then we talked about the three layers of the data architecture, and yeah, we talked about the three layers of data architecture as well, being the external level, which is for the users, you and I, accessing the code or the software or the app, right, on which we can access the data, right, that is stored on a server, right? And so the external level being the end users. And then we had another layer called the conceptual level, where you have people that are generally like administrators being in charge of the data that the users or the external level people see, right? And I mentioned that it could be the lecturer, right, who displays the content of a course on, let's say, on a platform, right? Like, for instance, Sakai or MIS, so that we, the users who are the external level people, go and access. So they can manipulate or maintain, right? But they can't change some things that are behind the scenes on the server or on the database system. You see, or the database management system. There are some people who are in charge of the server itself, who are in charge of handling the drives. Do you see the actual code behind even the app itself? You see, and these people are called the internal level. They are internal level, which is the third layer of the three schema architecture, right? So which is also a model, right? The tree schema we mentioned is a model. And we mentioned that these levels have a way of connecting themselves together, and it's through a certain superpower that enables it to connect to each other. How the conceptual level person is able to communicate something on that same platform without it affecting the user, which is the external level, and how the internal level is also able to change their hard drives or change their storage, because storage may get full, right? And so you may need to add up, you may need to decentralize or even centralize your storage, you may need to increase your capacity and things. How they are able to do that without also affecting the conceptual level people, right? And so we learned that that superpower is called data independence. Data independence. Oh, you see, it has started again. Please, I'm teaching at the moment, okay? So how data is able to communicate with a different level of the 3 layers, right, within the tree schema, right? It is tree schema because it has 3 layers or 3 levels, right, within which people or users, whether they are end user or the mid-level users, are able to access, or even the back end people. Do you get me? So from the user, the normal user, to the one who is managing, like the lecturer, or the one who coded or who created the app itself, or the ones who are at the back end of the whole thing, controlling how the system or the app or the software works. Do you see? This is the three. This is what we call the tree schema. It's not anything who they are like that. Now, this is what we learned yesterday. And how these 3 levels are able to connect with each other is what we call the each other without any disadvantage, right? Or without affecting the other. One is able to do something without affecting the other. You see, so we say that the data that they are doing is independent. You see, they are able to work on it alone without affecting another. So this superpower it comes in 2 main types, and we learned about the other one, the how do you call it? Two main kinds, right? We have the your friend is saying logical data independence, right? Yeah, logical data independence. Yes, also what the physical data independence. And I said that the logical data independence is the type of data independence where the conceptual level is able to make changes without affecting the external level. So if you are on the side of the middle, which is the conceptual level, and you're able to make changes at your level, and it is not anything, it's not like being affected on those who are using the software, or those who are using the system, the database management system. So, do you get it? Then we say that you are operating with it like within this context of the data independent, but yours is what? A logical data independence. Do you see? You are able to add even a phone number column so that the students will see that, oh, now there's the form we are filling, there's a new column that has appeared. It's called phone number column. Yeah, and we're able to flow, and it's not affecting anything. It's able to flow seamlessly. Do you get it? Then we say, oh, it is a logical, you see, logical data independent. And then we say the physical data independent, which is the second superpower. I'm saying superpower because that's not, yeah. So I'm saying it like that. What makes the three schema architecture work? The three schema we've talked about, that is the three layers: conceptual, external, conceptual, internal. What makes it work? This is the power that makes it work. And the second one was the physical data independence, which has to do with the change of storage from the internal level or the internal layer or the internal person, right? Or the back end person who is in charge of the server. So basically, this is what we spoke about. And then we also spoke about the client server architecture, where how do you call it? We spoke individually about the client and what it entails, what at all is the client, and what at all is a server. Sorry. I'm teaching at the moment. I'll get back to it. So yeah. So so we spoke about the client server architecture, and we mentioned that there are two separate things, right? Where I said the server is just a powerful computer that is running the database. The server is that system that is running the database. So that means that inside the server is those tools or those storage devices, right? That keeps the data. Remember, the server is like the system, right? Then you have within the system the cabinet, as I use the school cabinets in the beginning of the yesterday's lesson. So two common setups within the client server architecture. Whenever you see the client server architecture, the client server, when you say it, because they are two separate things and we are mentioning it together, we normally bring a hyphen in between. And so when we say client server, that's what we are talking about. So the client and the server, the client is the external level person. Do you see the external level person? When I say external, I'm talking about the user, the one who is using the Sakai, you and I. Do you see at the end of the food chain? You get it? Yeah. And then the server is where that data of what you are trying to access on Sakai, where is it stored? That system that keeps it is what we call the server. And so there are two types of systems. So we have the two-tier architecture, which we spoke about yesterday. And then we have the three-tier architecture as well. And we spoke about the two-tier architecture being the fact that in the olden times, your app, right, or your software, which is the client, talks directly to the server. You get it? Directly to the server. This is the olden days. So an old office program, right? On your desktop in those days, if you remember. And but the problem with this thing is that it's hard to manage. You see, many users connected at once. Do you see? You can't. The system will even slow down at a point. You get it? So there was a problem with that. You see, but it's simple because it can access directly. Do you see? But then we also have, apart from the two-tier architecture, which is the two-tier architecture, which means you have the client and then you have the database server. So client server, that means two-tier architecture. Client accessing the database server, right, directly. And then we have the three-tier architecture, which means that there are three different layers of the architecture, which means that instead of the client now accessing the database server directly, now there is a third-party agent in the middle, which is the application server. You see, it runs something like a business logic, right? And where it takes this and then it communicates to you. It takes this data from the server, right? And then it breaks it down into your understandable, view, right? And then you are able to access. So it's like a third-party person in the middle. You get it? So this was what makes it the 3-tier on the third layer. And this is the system we use in the modern day web applications, especially the web browsers. They go through this 3-tier architecture. Your Chrome, your Opera Mini, your Safaris, yeah, where this thing just goes through that, and then they break down the packets and they read everything. But you see, the problem with this modern thing is that now they have access to your information, whether you are sending or they are receiving. It goes through them. You see, that's how come they're able to send you adverts on things that you consume on the internet. They show you adverts that are related to that. So nowadays, with the advent of cybersecurity and all that, we are able to limit them through you see, whatever we do, they have access to it. So nowadays, what they are doing is that we are limiting them through legal means. You see, even though you have it, you cannot share it. But they share it, but it's low key. It's not as if the company that they will sell your data to, they will come to you and say, oh, they sold your data to us, your details or the profile of what you search for online, who you are, your password, your email, your bio data, where you come from, your full name. We have all of them, and so we have come. No, they also use it anonymously on different platforms for also decision making for businesses. It helps them a lot. So that's that. Maybe we are going to talk about that in another class. Anyway, so these were some of the things we did yesterday, right? Yeah. So today, we want to build on that. Now, after knowing all these things, the 3-layer, the 3-schema architecture, database architecture. Now, the question that comes is that since we know that this architecture is like a blueprint that we are supposed to follow in keeping our data, right, and storing things, what should the blueprint also follow? What structure? Even though the architecture is a structure, how? And yesterday I showed what a blueprint is and the term blueprint and where it came from. And so whenever I see a blueprint, you should be able to recollect, right? Good. Now, so whenever we are also talking about the database architecture and the various models that there is, what blueprint should the architecture itself also follow for us to even have the architecture itself to also for us to follow it? So which one is it also following? So what shape should it take? What pattern should it look? How would it look like? How would we be able to identify that this is the blueprint we must follow? Do you get me? What is the shape that it will take? Yeah. That's the that we should follow. So should the data be organized like a family tree? Do you get it? Should it have branches like a family tree where from from a two-sided one, right? Two-sided one, it branches into 4, 6, 8, or it from the other side, you know, since it's becoming a tree, you see, or it should become like a spider web, just like the internet, where everything is revolving around one thing, but we have a decentralized version of it. Or it should be like a simple grid row and column, like a table. And remember, I told you that whenever we talk about relations or relational, we are talking about a table. Okay, it's not, don't let the names or the terms beat you. Okay, now, whatever we are thinking, the shape or the pattern or the kind of shape of a table it should take, this, when we begin to talk like about that, then you should know that we are talking about data models. Data models. So this is the actual pattern. This is the actual shape that the blueprint, right, is laid upon. Do you see the blueprint, which is a data architecture, is laid upon? It's laid upon data models. So the database architecture is laid upon data model. Data model. Okay. So it is based on the data models that the database architecture are formed. Is the organizing pattern you choose before you build anything. Please, we have begun teaching again, so please start writing as usual. All right. Very important, because all these are not in the slides, if not even the ones I have created. Okay, so as we are writing, let's keep following. Now, so we are learning that that's exactly what a data model decides, is the organizing pattern that you choose before you build anything. Now, what is a data model? Now that I've explained it, but technically, let's put it in shape. So a data model is a blueprint pattern. It's because you know that one too is a blueprint for the architecture, right? Good. It's also a blueprint. That means that it's a standard. So whenever we say blueprint, we are talking about standard. So a standard way of describing, right, what pieces of data you have, right? What pieces of data you have. That's the customers, orders, products. These are all your name, you know. So when I come to you and I start saying dog meat, this thing, I'm just giving you data. It doesn't make sense. There's the same way if I come and say customers, orders, products, it doesn't make sense. It's when I start saying, oh, the customer, these are the customer names, then I start mentioning. Then when I come and I'm saying orders, you will not understand it until I say, oh, these are the orders of these customers that I came to mention earlier. These are their orders. So order number 1. So now orders are beginning to make meaning. That's when data becomes information. But for now, when we come and we say customers, orders, products, they are data, right? So it is, the data model is a way of describing pieces of data that you have. You get it? Powerful. So the pieces of data that you have, how do you describe them? This is the data model. It is a way of classifying, you see, or grouping. How those pieces are connected. It tells us the pattern. You say, make sure say data model, no, it shows us the pattern. You see, so the data that you have, how are they connected to each other? You see, what pieces of data do you even have in the first place? Whether it is customers, whether it is orders, whether it is products, whether you name it, you can create some yourself, depending on which industry you are in. Do you get it? And another thing it describes is what rules they must follow. So now that you found the name of your data, or you found the data, how do the data connect? Because the data individually, they must connect to form information. Now, what rules must they also follow? You see, these are the things that data models talk about. Please, are we following? Are we following? Anna Yatonsum. I'm breaking things down, pal. Yeah. So I'm gonna come here very soon. So let me continue. I know that we are writing. I want you to write because it would help you to, it will help all of us to, it will help all of us to remember when it's time to recollect, right? Because you are making the notes yourself. All right. Powerful. Let's continue. So the data model, no, is a pattern upon which we are able to connect the data to know even the data, what data we have, to even be able to connect the dots to see how they are all connected to each other. And then we are able to know which rules they must follow. Do you get it? So you think of it like building of a house. Before you buy bricks, you choose a style, ranch style, 6 inches blocks, you know, and so on. So even before you buy the bricks, yes, you have the plan of the house. You also need to choose a certain type of blocks. So this one will be the basis upon which your plan or your foundation is made. And this is what we are talking about. Why do data models matter? Why do data models matter? Why are we talking about database architecture and all of a sudden we are talking about data models? Oh, I'm sorry. I'm so sorry for this thing. This tone cry, I need to change them. So, as I was saying, the why at all do we need to talk about them? Why is it important? Do you see? So now we're about to do a little bit of a history. So in 1960s, let's talk about the evolution of data models. Okay, the rules, how we connect data, where it even came from. So in 1960s to the 1970s, so 1960s to 1970s, computers were rare and very expensive, right? Only few people had it. Only few people had it. Uh, you know, whenever, if you notice, whenever a new technology comes, whenever a new technology comes, it's very, very expensive, right? It's very, very expensive. And it is very also hard to get. You get it? It takes time for it to lose its value. And when it loses its value, they're able to produce more, and more are able to buy it all over the world, and they make their monies. And so when computers were rare and very expensive, the early data models were rigid. That means that they were good for only one specific job, but impossible to adapt. They were computers in those days would perform only one task. Do you get it? Uh-huh. If it is for calculation, this computer calculation. It was later that I think in the 90s or the early 2000s that computers started being like playing music at the same time, doing calculation, doing office work at the same time. At first, computers would do only calculations. Later, different devices for different purposes were created. Then later, they added all of them together. So if you look at it in that sense, you could see that in those days, computers were performing specific instructions only. So this is what I'm talking about. All right. So now, 1960s, right? The first model is called the hierarchical model, right? It looks like a family tree. Let me see. Let me see if I can get the hierarchical model. Hierarchical model. One here I'll be called technical. Hierarchical model. So it looks like a family tree. So let me show my screen. So let me show us. I'm posting something on the page today too. The people will be saying, what at all are they doing in the class? Every day they have some image. Oh, Lord have mercy. So today, let's look at it. I'm posting something on the page again. Say, Ebenezer, it's your phone now accessing. Mr. Nyako, is your phone able to see is he here? He's not here. Okay, good. So, you see that when I come to you, if you are looking at the image on the page, if I come and I say John, you will not understand. But when I if I come and I say CSE, you don't understand. When I say CA, you don't understand. But when I begin to connect John to CSE and CA, right? That CA, which could be the name of a place, right? Or the name of a state. And I'm able to associate John with it, or it's able to associate John with itself, or John is associating itself with the state and maybe the locality, then we know that, oh, John is actually coming. And then you are able to know that, okay, John, it is through Gami that we got to know about John. So in a way, we are connecting. But what we are trying to know here is that there is a particular way, right? And there's a particular style of gathering the data or connecting the data together. And it's through what? Like a tree form, because it's talking about one thing. So when we are talking about a topic root node, then everything related to it will be on the same thing. So in the past, computers were talking about one thing. If they will do calculation, they are doing only calculation. Do you get it? And so they would normally go with a structure that would look like a tree model, right? Since we are all coming, just like we are all coming from Adam. So if we are to do the tree, everything will come from Adam, right? So that is how everything is. But if we are to do something like the modern day thing that we call the internet, which is not coming from one source, the internet is coming from multiple sources. So if we draw it, it will not be a tree, right? It will be something like a web, spider web, because it's decentralized all over the world and we are all accessing it at the same point. Those who join my masterclass on how the internet works, you understand more. Otherwise, I would ask you to fetch that info and understand deeply how the internet works. All right. Yeah. So it uses, that's why we even call it web, World Wide Web. So that's the difference between the olden days and the modern days. But what we are talking about is the hierarchical model, right? Hierarchical model. Hierarchical model. This was the 1960s, early 1960s. So and it came in the form of the family tree. Hera. So when we say this disease you have is hereditary. It means that you inherited the disease, or it's in your blood, it's in the family. This thing is hereditary. That means that this character or this thing it's a family thing. You took it from your mother took it from this took from that, and so on. Like, yeah, like that. You get it. So there is a way and manner we fetch that data, and it comes from one source, and we call it the hierarchical model, which is the family tree. Are we following? Yeah, this is the first method. This is the first model that came, 1960s. So the shape of it, an upside down tree, right? Each child record was exactly one parent. You see. Real world example is a department that has many employees. This is another example. A department that has what? Many employees. So the department will be the parent. You see. And then the children will be the employees. So that's how we explain the family tree. So there is a parent and there is a children in this method, right? Good. And then we have let me do an analogy. The mother and the children, Adam and us, we are also the your mother will be the parent, and then you will be the children. So that department that we are talking about, any data that will come from that department will be the children of the department. Do you get me? So there is the pros and cons, good and then the bad. The good side of it, of this model, the hierarchical model, the good side of it is that it's very fast and simple because it has a source. Only one source to fetch from, the parent. It just goes, gets it and it's done. And it's only centralized on one particular thing. So in case you have to run a search for your data, because it's a database thing, if you are looking for a particular data, it's very simple to get it because you are focusing on one thing. Do you get it? But the side effect of it being fast and simple and one way is that is extremely inflexible. You can't twist it to do any other thing. It's just one way. That's all. The good side, another good side is that it's easy to understand. You get it? It's easy to understand. And then the side effect is that it cannot represent many-to-many relationships. When we say many-to-many, we are talking about the fact that the parent is not a mother. It's not just one department. It is a lot of departments connecting to another group of departments, not just one department, maybe 4 to 5 departments connecting with another, maybe 4 to 5 departments or even more. So this is what we call the many-to-many relationship. And that one, you can't use a tree model to explain. We are sticking with the tree model, which is the hierarchical data model. And that one is just one to many. We all come from one source. You came from your father. Your mother there, she just carried you. We all came from our fathers, right? So our mothers were hosting us. Our mothers were hosting us. They just fertilized us by the grace of God, and we are here. On a lie. Yes. So it's just one to many. So your father is the source of 4 children, depending on the number of siblings you have. So the hierarchical model, which is the early model, data model, that one is one to many. You see, but there are other models, especially the recent ones, where we deal with large sums of data, and you need to be able to access from multiple sources to other sources. You see, fetching from here. As we are talking, people are fetching data over the internet from many, many different sources, like the way Google will fetch from here and there and there and there, and then feed you with one information. Do you get it? So that's what we're talking about. Now, but that one is the modern one, and it doesn't it's not to do with this old type, right? Easy. Another advantage is that it's easy to understand the old model because it's simple. It's easy to understand. It's used by IBMs and IMS database. You know, these IBMs in IBM people, they had a very strong foundation. They are still in the market. They are still in business in different angles. Okay, but in those days, they almost own everything about computers. Do you get it? So their systems, right, are able to access these types of data models, right? And but the side effect of this data model that is that when you change the structure, right? If you change something around it, everything will break down. You see, it's for olden days. You don't stress it. Basically, it's not supposed to be stressed. And then we have the network model. The network model is what we call the spider web. It looks like a spider web. The network model is what we call, it looks like a spider web. Let me see if I can get a picture for you. The network models. So let me use this, right? Let me see if you understand it. I don't want anything that will confuse you. So when we talk about the internet, okay. Let me, so let me use this one so that you understand it better. Better. So on the page, I'm posting another image. So you can see from here. This picture is showing. So this is how the web, the spider looks like. I used the how the internet works. This is the modern day. You see, with that, it's not dependent only in the one in the middle. You can fetch data from the green side if you are from the blue. You can search, they can communicate. Even on the blue side, 7 can communicate with 16. 7 can communicate with 8. 8 can communicate with 2 by passing through, let's say, 3. 8 can communicate to 2 by passing through 3. You see, so it will come from all the way from 8, then 3, then 2. You see, if 8 wants to communicate with 1, it can go through 3 and then reach it to fetch its data. But if the system is busy, right, then the web module is designed in such a way that instead of going straight to 831, if the system is busy and there's too much overload on 3, it will go, and if it has to fetch data from 1, it will go through 9. It can go through 9, then 10, right? Then 4. or it can use 8.3, then it will go to 4, right? And then go to and fetch the data. So it's like the modern day way of accessing data has become more intelligent. You get it? Hence, this is why we call our systems now, we are having intelligent data models, which we also call the artificial intelligence. It's the nutshell of artificial intelligence is that data is able to communicate with each other, you see, and able to relate well with each other and know which data each one is carrying. The ability to know and draw that blueprint for the architecture to follow up. Now, good. So, as we are continuing, let me go back. So the second model is the network model, network data model, network data model. And this one is was brought about in the 1970s. So before it became common in the 90s, people were test running it, right? Few people only had access to it. So it's the shape of a graph or a web. The rule that it went with is that a child can have multiple parents. No wonder we have so much divorce in the system. With the family tree, the rule, you remember that each of the models also have rule that it goes with. It's able to tell you which data at all we are supposed to deal with, and then which rule it must follow, and then how they are all connected. So the rule of the hierarchical method is that each record has exactly one parent. But with the network model, each child has multiple children, multiple parents. Your parents are many and the child is one. So, so you can see that, where is it? Let's go back to the graph on the page. When you open it, the child in the middle has multiple children. And it's amazing where it can feed information from, can go through here, go through there, and fetch a lot of data from different sources, right? Without pressure on just one. You get it? All right. So with this, we move on to, so a student can take many courses. That's the practical example. So you have many courses at your disposal that you have access to as a student. Accessing the portal, you can access many courses. You see, a course can have many students. So whichever way, this is what 1 is to many. The other one is 1 is to what? Many is to 1, right? Many is to 1. The children is to 1. The children is to 1. The children is to 1. Each child has one parent. Each child has one parent. Yes, so basically we can say 1 is to 1. Okay, the older one, we can say 1 is to 1. One child is to one parent. Okay, and then the other one will say, the network one will say what? 1 is to many. You get it? 1 is to many. 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 And I mentioned that with that, a practical example in database systems is that a student will be able to access many courses on one website. Many courses. Many courses. You see, so 1:many. This is the network model. And then now we graduated from the network model, which was also in the 1970s. The first model was 1960s, but we are still in the 1970s. In that same 1970s, we have what we call the relational model. The relational model. The relational model is the table model. Network model is the spider web model. Also in 1970, up to today. It's a simple table. So one more, it is through the use of spreadsheets, what we call something like the Excel is also through the use of tables. And we use it to arrange data. You get it? For analysis. You get it? And so we have the shape of it will be one or more flat tables like spreadsheet. And then we have a rule for the relational model. The rule for the relational model is that data is stored in rows and columns because it's table. On every table, you have a row and you have a column. So tables are linked by shared values, not by physical pointers, but by shared value. What it means is that when there is a column called, for instance, we are keeping data of students and the courses they are doing. We can have the student ID number, right? The value, we can give the value of a student ID number as a value 101, right? And the student name is Mr. Anand. The student name is Mr. Anand. And Mr. Anand, his course number or his course code, that's the course he's studying, right, is Dcit 211. You get it? Now, with this table, with this, we can draw something like a table. So now let's go to Excel and let me do something like a table form with these details. And the representation of it is what we call the relational model. The relational model. So let me open Microsoft Excel and share my screen there. All right. So onwards to the Microsoft Excel. Can you see my screen yet? So we want to do a table. Instead of typing, let me just paste them. So we can have something like this. Let me do it, Dcit 211. And the person's name is Mr. Anand, right? Is this how to spell Mr. Anand? I think it's 1A. Yeah. So let me bring Bob Santo. And then we give him a course code. The course code is Dcit 203. So whenever we see such information, can you see my screen? Or let me zoom in. Let me zoom in on the page so that you can see the screen well. Please, can you see now? I believe you can see now. Please, can you see the screen now? Hello. Hey, mekyerɛ me ankasa me ho adeɛ anaasɛ. So when we begin to demonstrate the table or interpret the information on a table like this, we are calling it relational database. We can relate Mr. Annan to the ID number 101. We can relate Mr. Annan to the course DCIT 211. They have things in common. Mr. Annan and 101 has things in common. Mr. Annan and 211 has things in common. And through the table, the columns here and the rows, you see, this is the rows and this is the column. Through the column C, we are able to identify the course code DCIT 211, and we are able to connect it to Mr. Annan. So because the table helps us to explain this data very well, this individual data, right? The data we have here very well, and we're able to relate with it. We call it relational model. Okay. This is why we call it relational model now. Relational model. Now, as you are still watching the screen, this data helps us to identify. So now, when we see DCIT 211, we know that we are talking about database fundamentals. And so whenever the course is seen, the code, we know that, oh, Mr. Annan has to do with this course. And he's studying this course. This is the course code. This is his course code. And this is his student ID number. You see. And we are able to identify each and every data that Mr. Annan is associated with. So let me add a column here. Let me spread this here and change the name to course name, right? Course name. And so this is another column I'm creating, right? So we'll call this place the database fund. And then we can give this place what a different course name. Right. So what we are talking about, let's just give it logic. Okay. So this table is helping us to do, what this table is helping us to do is that it's able to tell us, right? It's able to tell us that Mr. Annan is connected to DCIT 211, which is database fundamentals, and his student ID. So you see that this data in each box here, right, represented by the name cell, all right, they are all connecting to Mr. Annan. They are all connected. They are all related. That's the word we are using, right, today. That's the technical term we are using today. This whole thing is connected, and because they are related, we call them the relational model. Relational model. And you can only explain this into detail with the use of tables. That's why whenever we talk about tables, we are talking about relations. Please, are we following? Now let's go back to what I was talking about. All right. So, 1, 2, 1, 2. Yeah. So we on the practical side of things, you notice that it has to do with rows and columns for us to understand. So who invented the relational model? Let's talk about the rule. The rule for we talked about the rule of the first one, which is the hierarchical model, and which is 1:what? 1:what? 1:1. Each child is to one parent. And then we've talked about 1:many, which is the network model, also called the spider web model, right? And now we are talking about the relational model, which is the table form. And we are saying that this one, the rule, just a sec. The rule is that data is stored in rows and column. Data must be stored in rows and column. In rows and column. In rows and column. Rows and column. The rows are horizontal, the columns are vertical. Please notice. Now, in continuing, we say that each book is one row. Each book is one row. Columns are the title, right? The columns are like the title, the author, the year. In this example that I've given, the columns are student ID, student name, right? Course ID, course name. These are the columns. And then the row is what will contain the individual data for the corresponding columns. And that is it. So who invented this relational model? Who invented this relational model in 1970? There is someone we call E.F. Codd. E.F. Codd. The code is C-O-D-D. So let me spell the code for all of us. So the code is C-O-D-D. Let me get his full name. Let's fetch his full name. E.F. Codd. 1970. So his full name, let me mention his full name. Edgar. His full name is what? Edgar Frank Codd. That one too, I'm putting on the page. Edgar Frank Codd. Edgar Frank Codd. I've posted it on the page. That's his name. So this man is the one who said, no, this relational model, when we use the table form, we will be able to explain. So you can say E.F. Codd. So when we say E.F. Codd, he's the one we are talking to. He's the one who created the relational model to be able to use it in 1970. And we have been using it from that time up till now, until we created another one has come up. But let's stick with this one for now. We learned in the last two lessons on the other ones. But we are talking about the relational model, and he is the father of it. So you can see, all right, the data stored in tables linked by shared values, query using SQL. I don't want to go into that right now. So this is the father of it. Now, let's move on. So, he created it. E.F. Codd was a researcher, and he was working for IBM. In those days, they were on top of the world, right? As at 1970, he was still working for them. So at first, IBM ignored his idea, but his ideas were so powerful that they became a standard that everybody was using. Now, you see, one of the things that crashes empires is that we ignore little ideas. And that's how come empires come crashing down. And so if you look at BlackBerry, they refused to bend to the new world order, right? And so they faded away, right? Apart from the government of US chasing them down. Yeah. And then also Nokia and all that. Do you get it? So when these new models come and they are solving real life problems, we all have to catch along and flow. Otherwise, by the time we want to flow, it will be too late. All right. So now, what are the pros and cons of the relational model? The pros and cons. The advantage of the relational model is that it's very simple to understand because they are tables, you see, and then, but then it can be very slow. It can be slower than the web because for extremely large or unusual data, it will look very long. Do you get it? Because the table will go down. And so if we have to talk about IDs below student IDs, what if the school is having over 10,000 students? So will we continue to have a table? It will look so long and cumbersome and weird. Look at it as I'm going down. It will keep going. And you have all this data on a table. Nah, it will not help. It will not help. And so for large sums of data, the relational model wasn't working. And this is why these recent models that we are using for complex data came up. But until then, the relational model was also simple and better than the initial hierarchical, the first one, right, in the 1960s. Good. And so this is what they were talking about by saying it's simple, because the table is there, the name is there. If it's for just thousands of people or hundreds of people, you can just connect and then make your references from them. You get it. And so there's one disadvantage from the relational model. It uses an advantage is that it uses declarative language, which is SQL. Say what you want, right? And not how. You just, anything that you want to have, you need to quote it, right? Exactly as you want it. So if I want to fetch a particular data from this table, all I have to do is to just mention the name. If I want to search something, all I need to do is to fetch the name of something, and it will fetch me the exact detail I need. But how I got there, it doesn't show me anything. Any information we need is what we get when we search for it. So this is basically, I'll come to the technical meanings of these things. We've not gotten there, so it will look complex. So we are taking it step by step. Okay. One of the things is that because it is not too complex, you can't use it for videos or 3D designs or like those things that need a lot of many-to-many database systems, right? So it is not conducive for that, right? It's just a table form relational, and so it's limited in its capacity. And so that's about it on the third module, the third data model. But let's talk about the fourth one, which is object-oriented model. The object-oriented model was brought forth in 1980s to 90s, the early 90s. The object-oriented, the shape of it, or the pattern looks like a bundling data plus actions. So the object-oriented goes with things like Java, right? And Python. You see, the data are brought together, they are bundled together in one. You see, and it flows with actions. You get it? And so with this one, straight away, you can know that anyhow you want it, you can get it through commands, because you can use it to do almost anything, and it will be quite intelligent. And so it deals with objects. So the rule on this object-oriented model from 1980s to 90s is that each object contains both data and methods. It deals with how to search for your data, and then it also deals with finding the data intelligently. This is basically what I'm talking about. So it contains data and also its related methods. So the data is what we call basically the attributes, right? And then the methods will be the actions that it performs, you see, for the attributes. You get it? And so an example, let me give an example. An employee object, right? An employee object might have something we call like data, right? And then within the data, we have name, salary, because I told you that when we talk about data, if you look on the table, we are no more using table, but I'm just saying the data that you have are what the name, and then what else? The name, the ID number, right? The course code. So if I mention DCIT 211, it's a data. It contains that one, right? And not only that, it also contains the method. Not only the course name, not only the course code, not only the name of the student, not only the ID number, but it also contains how they are used to connect to each other. It tells you with this type of model, it tells you how, we were able to link Mr. Anand to DCI 211 through this algorithm, through this code. This is what works behind the scenes. The method through which we got there, you get it, is the code itself. And so this is what we call the methods. And apart from the data, we also know how we are able to connect the data together. And this is what we call the object. So we have the name, we have the data, and then we have the method. You get it? So you think of a car, right? When you think of a car, so I was mentioning an employee. When you think of an employee, the data will be the name, the salary, hire date, the date we hired the employee, his output. This will be the data that is relating to an employee, someone we have employed in it. When we talk about a car, the data about the car would be like the car color, the car engine size, the fuel level, the fuel capacity, the engine capacity. All these things can be individual data, right? The oil level, the speed of the car, the maximum speed, the mileage of the car. These ones can be data that we'll need about a car. You see, this is data. But when we talk about actions on the car, we will be talking about the actions or the method, right? We'll talk about the start. We'll talk about the brake, the refuel. You see, these ones are actionable, or the accelerator. These ones are actions. When you press, there's an action. When you press the start or you turn the start, there's an action. There's a corresponding action that takes place. These are the methods. So the actions are the same as the method. The data is the same as the attribute. Okay, so in a regular table, you only store the color. You only store the color, and that's all. You only store that, this is the engine size, this is the fuel level. But in an object-oriented model, you also store how to use the car. Step on the brake, Feel just a sec. Let me this. Yes, I'm back. Yes. So in the table form, the difference between this one and the relational model is that the relational model doesn't have to do with the extra details like the methods and then the actions, the methods or the actions, or the data or the attribute, because data is the same as attribute, methods the same as actions. You get it? So with the relational, you would have stored only the data, car, color. About the car, you would have stored the color, the engine size, fuel, speed level, capacity of the car, and so on. But with the data-oriented model, you would add the actions or the methods to it, and it goes together in a bundled data form. You get it? And so this is the object-oriented data model. Okay. Some of the methods behind the car would be start, brake, and all that. If it has to do with employees, you will have a data like name, salary, hire data, and so on. And then their methods would be to calculate for bonuses, because when you're talking about salary, bonuses could be part, calculate for income tax, which the government will take or the person, the employee might pay, change department. You see, these are methods on how things may be done behind the scenes on getting a particular data, because the salary is as a result of some additions and deductions. So for you to see the amount 1,005 or the amount 4,000, you would see that there are some details behind the scenes. There are some additions, subtractions, some divisions that goes on. This is what we call the attribute, the method. And so this is the object-oriented. All right. So what is the advantage of this? Or what are the disadvantages? The advantage of this object-oriented model is that it is great for complex data. As you can see, you can relate, because it can fetch you how something is done. You know the method of what something is done. You have the information of what happens behind the scenes before a data comes about, right? You can manipulate data behind the scenes to fetch a particular information that you need or data that you need. And so you are able to analyze complex data. You see, it's very, very good for complex data. You're able to fetch them. And so it will be good for data like multimedia, MP3, MP4 video. You can use it to even this how do you call it? This multimedia stuff. And then the disadvantage about this can be that this model never became a mainstream model. It never became a mainstream model for business data. You get it? For business data. For business, we didn't use it, but we used it for multimedia because it can really work within what is behind what. And so videos, pictures, and so on, 3D models, they were used for those things. And so in the corporate world, it wasn't really found. You're able to use it, reuse via inheritance because you are able to recycle it. You can use it over and over again. You can manipulate things, right? Because you know how it works. You can recreate, you see, and get some things out of it, right? And so these are some of the things with regards to the object-oriented data model, object-oriented data model. And the fifth is the fifth one is instead of it to be object-oriented data model, this is object relational model. Object relational model. With the object relational model, the shape of it or the blueprint of it is like the tables mixed with the object features. The tables, which is the relational model, plus the object features. What are we talking about? Let's talk about the rule first. The rule for this model is that you must start with relational model, as I'm saying, because this is together with the tables. But then you start to add the ability to store custom data types like images, arrays, or even small programs. You see, the ability to store custom data types. Now, in the real world example, Oracle lets you store XML or the JSON file format. And these are files that contains the data about the application or the code that you have written. The database, right, of the code that you have written. This is where the data is stored, right? The data of the program is kept directly, right, in a table cell. And so with this, you will notice that it looks like a spreadsheet that allows attachments. So unlike the spreadsheet you are seeing over here, it looks like a table, but this time you are allowed to add attachments like images, videos to it to better explain the data that you have. And so this is what we call object relational. So you have the object, which is the image, and then it relates to the data through with the table. And so this is what we call the object relational. Object relational. We have object oriented, right? And we have object relational. Object relational model. You get it. Using the table by using these images, arrays, or even small programs to illustrate, you see, the data you have, you see, through the relational tables. You get it. Powerful. And so it looks like that, like the spreadsheets, which are having attachments, basically. So you still have rows and columns, but a cell can now contain a photo. You see, can now contain a photo. So let me go back to sharing the slide on the page, right? So we are on object relational. You get it? So, and then apart from that, so basically, you still have the rows and the columns, but a cell can now contain a photo. Do you get it? A cell can now contain, or a mini calculator. So it is not limited to only the tables, but you can also add attachments to it. And this is what we call the object relational. And it goes with an example, real life example is the Oracle, what we call the PostgreSQL, and so on. Because the PostgreSQL, it lets you define a city type, a city data, right? City data type with latitude and longitude now, which is like the column and then the column and then the rows. The column, the rows is latitude now, right? And then the column is longitude now. You get it the same way. But then you also have the ability to add images. The same way with the JSON files. If you open it, you can see the location of specific files inside, in addition to other data that are found inside. You get it? Which makes references to where data is stored for that particular software or that application. And then we have the Dcit data model, which is the NoSQL, which we talked about in last lesson. NoSQL, which is the big data model. So this NoSQL, if you look at the evolution of database management system, this one was the last module that came in the 2000s to solve the relational models. Do you get it? What the relational model wasn't able to do, the NoSQL came to solve them, right? And it was much more able to attend to big data, national or intercontinental data, like the world data with the likes of Facebook, Google. You see that you have to do with the whole world almost. Google had to virtually download all the websites in the world so that we can have access, and they are able to connect our searches to this website. You see, so that we can be able to find the exact detail that we need. So as the model is being worked on, things are also changing. Now, the NoSQL model from the early 2000s, right? The object relational can also be a hybrid one because it deals with table and then the attachments, right? But the relational, how do you call it? The NoSQL model, right? This is the 2000s up to today is being used. So the blueprint of it or the shape of it looks like the document, right? It varies, but it varies from the documents, columns, graphs. Like it's a combination of everything together. It's a combination of everything together. Columns, graphs, rows, or key value pairs. You can add documents, you can add videos, it's a kind of system or database that you can have every file, every type of file within or embedded in it. Do you get it? It is able to have all types of storage within it or keep certain things. The rule with it is that sacrifice some consistency for extreme speed. Sacrifice some consistency for extreme speed and scale. You get it? Okay, so let's talk about it. There are four main types of this NoSQL model. We have the document store, right? Remember, you can add all types of files that we have listed so far in all the models. I said that you can store the pretty much the multimedia documents, JPEGs, and some of the multimedia formats. So you have the document store, we have the document store type of the NoSQL. An example is the MongoDB, which is used for storing .json files or documents, and then flexible schemas and so on. And then you have the common or the column store, which is Cassandra. One example is Cassandra. We can just check on that and see what it does. It's used for massive data across thousands of servers. So you have different storage facilities across the world, and then you have access to all these storages. You see, combined. You get it? Graph database. The graph database, an example is the Neo4j, F4j, Neo4j, Neo4j. Let me let this motor pass by. Neo4j, what does it do? When we talk about graph database, when you are doing a software and there's a graph, and you know there's a particular NoSQL type that we normally use. The Neo4j is social networks, right? Recommendation engines and so on. So what it does is that it's able to fetch data. It's able to store data with regards to these environments. So we have the document store, the column store, the document store for storing the JCL, the JSON files, .json files, like documents and so on, right? And then you have the column store for massive data across thousands of servers, right? And I mentioned Cassandra as an example. The document store, I mentioned MongoDB. The graph database, which is the Neo4j, which is an example for storing graph database, right? You see, for social networks and so on and so forth. Key value stores. We use Redis. Redis is an example. You see, for caching, for session storage, real-time leaderboards, and so on. So whatever program you are writing, where you need to store data in different types, whether it's a document store, whether it's a column store, whether it's a graph database, whether it's a key value store, you have these under the NoSQL data models to explore with. Do you get it? And it makes it more diverse to be able to analyze complex data in large volumes. Do you see? So with the relational model, a filing cabinet with perfectly organized folders, as I mentioned. When we talk about the relational model, we are talking about the filing cabinet, the table itself, with perfectly organized folders. But with the NoSQL, when we talk about it, how it's connected to the relational model is that it's like you think of it like a warehouse where you can throw your boxes anywhere. So it's like a big warehouse. You don't really have a compartment where you put your things in. You just open your warehouse and you just put something anywhere. But you have a super robot that will help you find where you have put anything. You get it? You just drop it anywhere. But there's a robot, you get it, that will help you to say, oh, you place this here, let me fetch it for you. Oh, you place it there, let me fetch it for you. This is different from the relational model. With the relational model, just like a cabinet, you know where you have placed it, and you have to keep all in your head. But with the NoSQL, you have all these systems in place where it will help you fetch what data and where you even placed it. You get it? So this is how it is. So the judgment is that it's not a replacement for relational, because by now people are thinking that then we should use the NoSQL and drop the relational model. You get it? But it is not a replacement for the relational. It is rather here to complement it. So what we must do is that we must use the relational for accounting. That is why Microsoft Excel, for example, is purposely used for accounting and so on. Nowadays, they are trying to add some, features that will help it do so many things, but it is meant for calculations and you must stick to it. This is why tables are able to explain these accounting models and corporate business stuff better than any other plain sheet. Do you get it? And so the relational model is still important up to this day, but it will still be used for specific things, whilst the NoSQL model will be used to complement it for other things. Do you see? Use accounts, invoices, student records, but not to a certain limit. But we'll use the NoSQL for logs, charts. If you want to create a social media account, which would take the whole world to be part of it, you would need these models so that you can be able to find complex data on that same platform. Do you get it? If it has to do with AI models that you are creating, you should be able to fetch data from a particular source, depending on where you want to fetch your data with the NoSQL, because you are able to fetch with it. Do you get it? And this is basically the 6 main types of the data models when we talk about the database models. All right. The relational model that I was talking about, you would realize that relation, so far the terms I've been using, relation is the same as table, right? When we talk about the student table. But another key thing going forward in this course that we are going to do is that we have something we call tuple, which stands in for role. So the role that we talk about in Excel, the row, ROW, is what we call a tuple in database management. A tuple. So when you hear or tuple, depending on where you went to school. So when you pick a row, a whole row can contain one record. We say a record because it contains individual data of multiple sections of data all together with that are connected. They are connected to one person. So you can see Alice, you can see Alice's ID number, you can see the course code, you can see the name of the course, all on one row. So when you pick it, that whole information you have there is called what we call a record. So the whole row is what we call in database as a tuple. And then the column is called an attribute, where you have the names of the records, individual records, the names of the individual data. You see, so the ID number itself, the name ID number, it's an attribute. The name of a person is an attribute. The student ID number is an attribute. The age is an attribute. The course name is an attribute, right? So all the titles within the column is also what we call the attribute. So when you hear a column in database, also connected to attribute. So tuple is connected to rows, attribute is connected to column. That's what we've learned today. Domain is where we have allowed values for a column. So age must be 0 to 20. The ages must be between, let's say, 0 to 120, because we know that human beings for now are not exceeding 120 years. So when you give a certain limit to age or a certain limit to a particular range, then we call it domain. We are within the domain of 1 to 119 years. You see, so we call that a domain. We are staying within that domain. And then we have something we call a primary key. A primary key is basically a unique identifier for each row. You get it? A unique identifier for each row. Student ID is an example of a primary key. You see, it never repeats. Your student ID is a unique identifier to the person. And with this one, you will never have anybody having that same information. And this is what we call a primary key. Nobody else will have that information or data. Do you get it? And then we have something we call a foreign key. The foreign key will be not in the row like the primary key, but this one will be a column. The foreign key will be in a column that links to another table. A column that links, so you can have another table somewhere, and then you have a particular column in the initial column that is linking a particular information within that table to another table in another location. And this is what we call a foreign key, because the data in that place may be relevant to the current table that you have. And so you place the foreign key there, and it's able to fetch information from that table and the current table. And we call those ones foreign keys. All right. A student ID, course ID, right, in student table links to another course table. Your course ID in the student table, your course ID, which is, let's say, Dcit 211, linking to another course table, okay, where it needs to come up to be able to link up with the course that you are doing to another one. You are needing that information that you have already used. You don't want to repeat it. So it makes reference from the previous one. And this is called the foreign key. So over there in that new table, the key has become a foreign one where it needs to fetch data from a previous one. And this is why it's called a formula. And then we have the schema, which is basically tables or blueprint, which we learned yesterday. And so these are the various models, and these are the terminologies within what we have discussed today. Today, we have learned that the relational model has to do with tables. It's the most common. We use it for banking, accounting, student records, inventory, but not too much of a data. And then we have the hierarchical, which is rare today, but it's very simple, fixed one-to-many data. You see, and we have the network, which is obsolete, right? We have complex navigation with many paths, right? Many paths. And then we have the object-oriented, right? Object-oriented, which has to do with the CAD, multimedia, engineering data, and so on. And then we have the NoSQL as a complement, right? Massive scale, social graphs, caching, right? So in one sentence, everything we have learned today is that a data model is the shape you choose for organizing information. The shape you choose for organizing information. What shape you take in organizing your information is what we term as data model. The blueprint is there, but the shape that the blueprint will take is what we call the shape that your architecture, your data architecture will take is what we call the data models. That is what your data architecture is following. You get it? The pattern that is following. So from rigid trees, which is the hierarchical method, to flexible tables, which is the relational, to ultra fast warehouses, which is the NoSQL, where you have robots, where I mentioned that you have robots to fetch the data, even though it has been placed anyhow in the big warehouse, unlike the relational ones that are placed in something like cabinets with names on them, right? Powerful. I wanted to give, this lesson has been very, very long, but I wanted us to finish the whole thing, and then I will do some questioning later on. Maybe we might go through one more time before we move to the next topic. And so thank you all for being here. If there are some questions you can ask so that I'll clarify them for you. If they are not, you can send them privately and they will be you will be attended to, God willing. Until then, I'll meet you again. I don't know what time I'll meet you, but I think Monday, God willing, I'll meet you so that we'll continue. We have to move quickly, and so bear with me for taking a lot of your time. All right. Thank you very much. I'll meet you again if there are no questions another time. Until then, I'll see you on Monday. It is bye for.
Bye bye. Thank you so much.